enough to create the final state particles. Or in fact, it should be the maximum. I should have put it's the maximum of MA plus MB or MC plus MD. Whichever of those is greater is the threshold. Now, instead of writing, as we'll see, the variables in terms of the center of mass energy and theta, it's convenient to use the cosine of the scattering angle. And so the cosine obviously runs from -1 to +1. So this is the physical region. When it's in doubt which angle it is, I'll put a sub S on there to tell you it's the scattering angle in the S channel. Okay. Now, as you know, S is a Lorentz invariant, but the scattering angle is clearly not a Lorentz invariant, and physical quantities are functions. Not only are scattering amplitudes Lorentz invariants, but they're functions of Lorentz invariants. So, as you almost certainly know, you can define another Lorentz invariant, T, which is PA minus PC squared. So essentially it's the momentum transferred between one particle A and particle C. And then you see immediately, because it involves the scalar product between A and C, it involves the cosine of this scattering angle. And if the masses are equal, if, for example, if the mass of, just to make it simple, MA equals MB equals MC equals MD is equal to the same mass, then T is equal to -2 times P squared, 1 minus cos theta S. Okay, where that's the same cosine. And you see that comes about because of the scalar product between those. If you dot this one into this, you get PQ cos theta. So this is a Lorentz invariant way of writing the scattering angle, and so then the physical region can be drawn in a different way, in which instead of writing S and the where shall I do it? I'll do it maybe here. We can draw the physical region instead of, let's put S this way rather than the square root of S, and write T that way. Then the physical region in terms of S and T is this region, and what the straight lines, so these are the boundaries, these correspond to cos theta equals +1, this is cos theta equals -1, and these are the lines at a fixed energy. So this scattering region becomes that scattering, is the same mapping of the same one. Now, as you probably know, it's convenient to introduce a third Lorentz invariant, which is clearly not independent, which is PA minus PD squared. And then these are related to each other, and it's a simple piece of algebra, and I leave that as an exercise for you. If you haven't done this, it's very simple to do, that this is true. So that's the first exercise. Very simple. And the simplest way to do it is to write S is equal to this, T is equal to this, U is equal to this, and add them together. And you will see that it comes out to be that answer. Now, remarkably, this is the S-channel physical region that I've drawn here, but there is another region, which is where T, where the square root of T is the center of mass energy, which is for the process. So the S channel is AB goes to CD, where we have a antiparticle of C going to antiparticle of B, D. And then T is the square root of t is the center of mass energy for this process, and S, instead of being now, is related to the cosine of the scattering angle in the t channel. And that has another physical region, which you can draw also on this, and I perhaps have just left myself enough space, where these would be the fixed energies of t, another physical region. And then in this plane, there is a third physical region, which corresponds to the process A d bar goes to B bar C, or whatever, where U, or the square root of U, is the center of mass energy. And then that's a region that's drawn over here, and we'll draw it a little bit more precisely in a minute, because instead of writing the variables, the Mandelstam variables, ST and U, at right angles to each other, it's better to draw them at 120 degrees to each other. So now, if you draw S in this direction, then this was the S-channel physical region if the masses, well, maybe I should make the masses unequal, and then it's actually more interesting. So S is there, T is measured from this line, and this U is measured from that line. So this is the line S equals 0, that's the line T equals 0, and that's the line U equals 0. And then it's just a piece of simple trigonometry that the sum of S plus T plus U, if the lines are 120 degrees to each other, are equal to a constant, where that constant is the same as the height of the triangle, is that same number. So then we have three different physical regions. Here is the S channel, and those lines correspond to a fixed energy in the S channel going from the forward to the backward direction. So this is AB goes to CD. And then there is another region here where now T is the center of mass energy, and that's AC bar goes to B bar D. And then a third one over here, which corresponds to AD bar goes to C bar B. Goes to B bar C. Now, how do you know where these regions are? One of the remarkable things about relativistic processes is the first thing is that it's the same scattering amplitude that describes the reaction in each of these physical regions. It's the same function, but it's to be evaluated in different kinematic regions. So it's a function, a complex function of S and T and U. ST and U are obviously related to each other, and you have to evaluate them in these three regions, and they are the same function, but just evaluated in different places. Now, the first thing is, how do you know where these boundaries are? Now, they are defined. When the masses are equal, it's very easy, but when they're unequal, how do you do this? So the boundary, the physical region, the physical regions all correspond in terms of center of mass for p squared, q squared, and sine squared theta positive. So in any channel, it's a physical region if the momenta are real, which is what p squared being positive means. So the initial state, the final state, and the sine squared of the scattering angle should be positive. In fact, it should be between, in this case, they should all be positive, and sine squared theta, I should say, is between 0 and 1. So that defines where the physical regions are, depending on which frame you use. And to define that in a Lorentz invariant way, consider a vector which is normal to the scattering plane. So the vectors momenta, A, B, and C, form a plane. And there is a normal to that plane. And the normal to a plane in 4 dimensions involves, just like the normal to a plane in 3 dimensions, involves a cross product or whatever. PA lambda, PB mu, PC nu. You could choose any 3. Okay, why did I not put D there? Well, it's the same vector. Because, well, let me. Who doesn't know what? Does anybody not know what this is? It's the generalization in 4 dimensions of the epsilon ijk. Okay, so it's called the Levi-Civita tensor. Now, a simple way to see what this is, and why it's equivalent to what I just wrote down, is clearly you can add, for example, to A, PB, because what is the term that you've added? You've added a cross product between PB and PB, and by definition that is 0. Okay, so if any 2 vectors are the same. Now, if I work in the S-channel center of mass, PA plus PB is very simple because it only has a time component. So that tells us that the first one has to, this can only be the kappa, this has to be 0, this component has to be 0, and this is root S. So then, the only non-zero one must mean that mu and nu are, only have components 1 and 2. So this PB, since we've used the 0 component, must involve the 1 component. So we get minus P there. And then this one has to be the 2 component, and that's Q sine theta. And then the only one that is non-zero is N3, because they all have to be different numbers. So you see that the square of the vector n, the square of the vector n, n squared, which is minus sp squared q squared sine squared theta. Okay. And the boundary of the physical region corresponds to where n squared is equal to 0. So the boundaries are when n squared equals 0. Now, you can do this in any frame, obviously, and write it in terms of Lorentz invariance. And that's the next exercise for you to do. And in fact, it's related to something known as the Kibble function. Which is equal to 4 times, it may be minus. There may be a minus sign, but I will let you check that. Which is a matrix. If I write down, I won't write all the elements because it's too much to write, so I'll write one of them. So you can show, I think you can work out for yourself what the other elements are. It's the determinant where these are PA, PB, PC dotted into PA, PB, PC. And the boundaries correspond to when this function is equal to 0. So let's just write down what they are in a couple of cases. So if it's particle A goes to AA, and these have mass equals m, well, it doesn't matter. The boundary is STU equals 0. So that's nice and simple. In other words, it fills each of these regions here. Fills each of those regions. Now, if it's pi n to pi n, where this has mass mu and this has mass m, then it's STU minus or equal to T. Yes, maybe there's a better way to write it. Sorry. T times SU minus m squared minus mu squared. So one boundary is t equals 0 and the other are two hyperbolae. And then let us do another case where there are again two masses, but three of the particles have the same mass. So it could be the eta, the omega, any particle that, and this has mass m, and the pi's have mass mu. And then it's STU minus mu squared, m squared minus mu squared, squared is equal to 0. So, exercises for you to do is to work out each of these. So this is exercise 2 or 2A, and exercise 4 is to do that. Now, in the last case, something special happens. We've seen that there are 3 physical regions, but sometimes there are 4. Now, who knows, can tell me when that happens? Somebody knows. Please. Exactly. So in this particular case, if the mass m is bigger than 3 mu, then another region appears in the middle of here. So let me draw it bigger. So that's inside there. I can't quite draw it inside there. And that corresponds to the decay. Eta goes to 3 pi. And again, it's the same function that describes what's going on in each region, just evaluated in a different way. And so an exercise for you is to see why. In fact, the physical regions correspond to this being greater than or equal to 0. Why, when m is greater than 3 mu, is there a 4th region? Fourth. Now, an example, that's properties called crossing, that they are all related to each other. And a process which is fictitious, but because one can't actually do it experimentally, but would illustrate the point, would be if in the S channel, let's choose a weak interaction. I don't know if this is what I want to do, but let me... What shall we choose? Well, maybe I want to choose this to be the T channel. Well, it doesn't matter. Let me choose. Let me choose the process to be this. So imagine that's the S channel. Very difficult process to do experimentally, but then there is the T channel, which is mu plus nu mu goes to E plus nu E, and the U channel is mu plus nu E bar goes to E plus nu mu bar, and then the decay region in the middle is mu plus goes to E plus nu E nu mu bar. So there are four processes related to each other, and in electroweak theory, because the weak coupling, the Fermi coupling constant, is small, we can represent this process by this Feynman diagram, where a mu plus goes to a nu mu bar, and this emits a W plus, and the W plus, so this is a E minus goes to nu E. Okay, if I've got that right. So this same Feynman diagram, lowest order in electroweak theory, describes what is going on in each of these regions when you evaluate that simple Feynman diagram in the four regions that are related to each other. Okay. So normally in the strong interaction, you can't draw one Feynman diagram, but in electroweak theory, it makes sense to do that. So crossing is a remarkable property. It's only a process of relativistic scattering that in fact these processes are related to each other and described by the same scattering amplitude. Okay. So now let us imagine that we measure some scattering amplitude, or we measure some cross-section, and we want to know what the scattering amplitude looks like. So let's see if we can do that. So can I erase this now? Yes. Okay. So an amplitude, as I said, is the probability of scattering. So what we're going to do, amplitudes from cross sections. Okay. So if we consider spinless particles, and for the moment, let's say the process is AB goes to CD. 2-to-2 scattering, it doesn't matter what the particles are. And we measure some differential cross-section, which is the probability of scattering happening into some solid angle. And we do that in the center of mass frame. Then in terms of the variables we just had, this is equal to Q, the free momentum of the final state particles, 64 pi squared PS times the modulus of the amplitude, which we're going to write as a function of S and T, or in the S channel, the scattering angle theta S. And in fact, rather than theta S, we're going to use F and Z, or Z, which is cos theta. The scattering angle in that. So we measure some differential cross-section as a function of cos theta. So it's some given energy from +1 to -1. It's usually drawn that way round, going from +1 to -1, because in terms of the scattering angle, that corresponds to theta going from 0 to pi. So we usually put the forward direction, the +1 end at this end. And then the differential cross-section at some energy might look like this. Let's imagine it looks like this. It could be something more complicated, but there's an example. And what we want to know is, if we measure this, how do we find what this is? Okay, so that's what we're going to try to do. So, if it's spinless, nothing will depend on omega, it depends on cos theta and phi, the azimuthal angle. But if there is no spin, then nothing depends on the azimuthal angle, so we can integrate by 2 pi, so that's easy. So d sigma by d cos theta is q over, and where these factors come from, well, if you don't know, you'll have to look in some textbook, I think. So, at a given energy, let's represent this dependence as a polynomial in cos theta. So we have at a given energy, we've got some angular dependence that looks like this, and we represent it by a polynomial. It will stop somewhere, because you won't be able to resolve how many wiggles there are. The more higher powers of z you have, the more wiggles you have. So a formal way to do that is to represent d sigma by dz as equal to a sum over n. Actually, well, let's first write it generally. To write the differential cross-section in terms of Legendre polynomials. So these are the Legendre polynomials. And what this does is it tells you the differential cross-section, which is the modulus squared of an amplitude, involves a function of the center of mass energy and a function of cos theta. And by writing it like this, at each energy separately, you factorize the dependence on the energy from the dependence on angle. And you write the dependence on angle in terms of known functions. Now, you can determine the HNs, if you remember the property of Legendre polynomials, and hopefully you do. Who can tell me what I have to write on the other side of that equation? You know the answer. No? These are orthogonal to each other, unless m and n are equal. So they're equal to delta mn, which says the answer is 0 unless m equals n. And there is some normalization factor, which is 2n plus 1. So you can use that to tell you what these HNs are. So that tells us that these, which are called moments, are equal to half the integral from -1 to 1 dz Pn of z, the differential cross-section. So you take the differential cross-section and multiply it by the Legendre polynomials and integrate from -1 to +1, and you determine what these coefficients are. These are called moments of the angular distribution. Now, I'm sure, since you must have all studied the hydrogen atom, you know what the Legendre polynomials are, even if you've forgotten. But they're the simplest orthogonal polynomials that you can write down. So let me write down the first three of them. And so on. So they all have the property that if you integrate any pair of them where m and n are not equal, the answer is 0. Now, since you're going to do this for real data, I'm going to take the data, put it in here, and evaluate this integral with n equals 0, 1, 2, 3, and so on. At some point, they will get so small, because they each one has, the higher powers have more and more wiggles in them, they will be equal to 0. So in practice, Hn will be equal to 0, or approximately equal to 0, for n greater than some number 2 times capital N. Why it's an even number, we'll see shortly. Now, this is a step towards determining what this amplitude is. So measuring the cross-section gives you the modulus squared of an amplitude, and the physics resides in this amplitude. So how do you find out what that amplitude is? So let's imagine, just as an example, we just already had that at the beginning. Imagine in the process ABC goes to CD, there is a resonance with spin L. Then this will correspond to a term with a particular angular momentum, and the eigenfunctions of angular momentum are the Legendre polynomials. So f of s and z, or z, itself can be written as a sum from L equals 0 to infinity, 2L plus 1, FL of s, PL of z. So the amplitude, these Legendre polynomials, are the eigenfunctions of angular momentum. So if you want to know what the scattering is that takes place with a given angular momentum, 3, you want to find what F3 looks like as a function of energy. And F3 has some characteristic angular dependence, which is given by the same Legendre polynomials as the ones we had there. So, how are we going to find these? Now, because the Legendre, that we started from the differential cross-section at a given energy, so S is fixed, writing it in terms of an expansion in terms of Legendre polynomials. And we can find each of the numbers that sit in front there. And depending on how many wiggles there are, essentially because these functions oscillate, with more oscillations the more n's there are, you can determine what these coefficients are. Now, because the Legendre polynomials are polynomials, you know that the differential cross-section can equally well be written like that. That would be just writing it out. We've said that there are up to 2n are non-zero. So that means there are here 2n plus 1. We've written d sigma by dz, or dz, in terms of 2n plus 1 real numbers. Real numbers at a fixed square root of energy. Now, what do you know about a polynomial? If you have a linear function, how many zeros can it have? Don't all shout at once. It can have 1 zero, if it has any. If it's a quadratic, how many roots does it have? 2. If it's a cubic, it has 3 roots. You recognize something. A polynomial of order 2n has 2n roots. So I can write this as a product from I equals 1 to 2n. Where this is cos theta, these are the zeros, there is some number that sits in front. We'll worry about the number in a minute. To remind you, this is cos theta, this is the position of the zeros, and they're functions of S. So each of these coefficients is different at different values of the energy. But the differential cross-section is a real number. So then, this has got to be real. And that tells us that half of the zeros must be the complex conjugate of the other half. There are particular cases where 1 0 could be real, but that's a very special case. So in fact, this is equal to, again, some number. Product from 1 to n, z minus zi of S, z minus zi star of S. So if you have a real quadratic, it will have 2 roots, and they've got to either, both of the roots have got to be real, or if they're not real, they're the complex conjugate of each other. And the case when they're real is rather special. Will only happen at some particular value of S that can happen. Now, what do you see we've managed to do here? We've written the differential cross-section, which we know is a modulus squared of an amplitude, as a function times its complex conjugate. So that tells us how we can find the amplitude. Okay. Let's take care of the number in front. Let's do that. So, let's take out at the front the differential cross-section in the forward direction, which corresponds to cos theta equals 1. And then we have that just acts as a normalization. So that's just taken out So this is just a number. Okay, when cos theta equals 1, it ensures that that factor's 1, and so it's equal to this differential cross-section. So we said that the differential cross-section was written in, contains two n plus 1 real numbers. So where are those two n plus 1 real numbers now? There's one real number that sits in the front, and then there are n complex zeros. So that's two n plus 1 numbers. Okay, so there are n complex zeros, i.e. n complex zeros plus 1 normalization. Which implies 2n plus 1 real numbers. So now how do we find the amplitude in which physics resides? It's some number in the front, which is just kinematics, and a modulus, a function times its complex conjugate. So let's write that down. So we factorize f of s and z equals f of s and z at the forward direction the amplitude can be written like that. Okay, that obviously satisfies, that's essentially the square root of that equation. Okay? Now, one piece of physics and one piece of mathematics. Let's do the physics first. Maybe it's convenient if I do it over here, because then I can keep what's on the board. What are these zeros? We've done this at 1 energy. And I said the differential cross-section, here's an example. So there's plus 1 and there's minus 1, and this is cos theta. The angular distribution, let's imagine the angular distribution look like that. So that's d sigma pi dz at some particular energy. Now, what are these zeros? We can pick out, the way I've drawn it, two of them immediately. That where that dip is the real part of Z1. And this dip is the real part of Z2. There may be many other zeros, but they may be outside the region between plus 1 and minus 1. But they correspond to the dips in the angular distribution. And I already mentioned that dips in the angular distribution are related to the spins of the partial waves or the resonances that contribute. Now, what about this height? Imagine that, so here is one of the zeros, Z1. Imagine it was on the real axis. What would happen to the differential cross-section if it was on the real axis? The dip would go right down to the real axis. So that height is related to its imaginary part. So how far it is away, that height, if we've got a colored chalk, that height is related to the imaginary part of Z1 squared, and that height there is related to the imaginary part of Z2 squared. And that's because if the imaginary parts were 0, the dip would go right down to the axis. So what you're doing here is mapping out the zeros of the amplitude. And the zeros will be in particular places at a given energy, and at other energies they're at other places, and they move. So that's the physics part. And in fact they move continuously. So maybe I put that here. The zeros in d sigma dz move continuously with energy. With S if it's in the S-channel center of mass frame. Now, I've got to stop in a minute, haven't I? Okay. Now, do I know that this is the amplitude? This clearly satisfies that equation. Okay. But could I have written something else down? Well, let's imagine it's a simple case there where there are only 2 zeros. So there's z minus z1, z minus z2, z minus z1 star, z minus z2 star. I only know the modulus squared. So clearly, I could have swapped one of these for its complex conjugate, and it would have still satisfied it. And if I can do that for every zero, and if there are n of them, that means I can write down 2 to the n amplitudes. So, you can swap Zi for Zi star for I equals 1 to n. So there are 2 to the n equivalent amplitudes. Equivalent, or 2 to the n amplitudes, that describe exactly the same differential cross-section. This is called a discrete ambiguity. So in some process, like proton-antiproton goes to 2 pions, a simple 2 to 2 process, not very far above the threshold, there will actually be 10 zeros. So you'll have 2 to the same from the differential cross-section. You can write down 2 to the 10, 1,024 amplitudes that describe exactly the same experimental data. How do you know which one is the right one? Only one of them describes physics. So how do you know that? That might be a challenging problem. The second thing, this is a discrete ambiguity. I wrote down here the amplitude in the forward direction. But we measure here the differential cross-section, which is the modulus squared. And so I know this number here that sits in front, it gives you the modulus squared of the amplitude, but it doesn't tell you its phase. So this, where can I write that? Here. There is also a continuum ambiguity. Only the modulus of the forward amplitude is known, not its phase. So we again need additional information to know what that is. Now, since that's almost a good place to stop. What I would do next, and what I'll do tomorrow, is to tell you, to finish this off, that these zeros that move in what's called the Mandelstam plane across the physical region connect the dynamics in one energy region to what happens in other energy regions. Namely, these zeros, these dips, move continuously. And though it looks at every energy as though there are a large number of ambiguities in determining the amplitudes, because they move continuously, they're connected from one energy to another. They don't just suddenly jump from one to another. And we'll see how that happens and what dynamics they connect. Okay, so maybe I should stop there. Okay.